Welcome to our first contributed talk, Stefan Plachta. He's from Tampere University. He will give a talk about photonic implementation of quantum finite automata. Yes, Stefan.
Hi, thanks for the welcome. So I'm presenting some research about using transverse spatial modes of light as a quantum finite automata. First, what is a finite automaton? It's a fundamental computational device that takes an input string, operates on it based on what the input is, and outputs a yes or no answer. We use it to do a prime number search. Structured photons arise from solutions of the Plachta wave equation in cylindrical coordinates. At least the Laguerre-Gaussian modes are the solutions in cylindrical coordinates. And the source of our photons is a type 2 spontaneous parametric down conversion source, and we put individual photons into superpositions of LG modes to use to perform computations with 1, 2, 3, or 4 qubits. So here's a state diagram of a classical finite automaton, which are used in computing to answer questions like, is this a valid email? Do the passwords match? For the prime number promise problem, the state diagram has one accepting state and a number of rejecting states equal to the prime number minus 1. So the thing about this is that in a classical finite automaton needs at least as many states as the prime number you're searching for. So if the prime number is 11, it needs 11 states. One of them is accepted. Now, with quantum finite automaton, we want to demonstrate that we can use a smaller state space than is required classically using the superposition principle. So here's a state diagram of quantum finite automaton. There's an input string, and it performs a unitary operation depending on what the character is. For the prime number promise problem, all the characters of the input string are identical, so there's only one unitary operation performed, and then it produces a probabilistic output based on whether it's measured in accepting state or rejecting state. And here is the promise problem represented as a modulus. So what are structured photons? Like I said, solutions of Plachta wave equations, cylindrical coordinates, they're governed, the Laguerre-Gaussian modes are governed by the Laguerre polynomials, which have a radial index P and an azimuthal index L. P describes the number of rings as you go out along a radius, and L describes the number of 0 to 2 pi phase ramps as you make one rotation of the azimuthal angle. All these modes are orthogonal. They have high dimensional states, infinitely many of them, and we use them to encode single photons with quantum states. So here's what an LG mode with P equals 0 and L equals 1 looks like. L equals minus 1, you can notice that the phase ramp is going in the opposite direction. The spectrum is minus pi pi. And here are some more interesting modes. Here's with L equals 4, and P still equal to 0, so you see 4 phase ramps in one rotation of the azimuthal angle. And with P equals 2, there's 2 more rings. And yeah, but let's get to how we use them to perform calculations with qubits. So we can represent them on the block sphere. If you superpose these two modes, you get a new basis on the XY plane, and we use the basis that's along the plus and minus x-axis. So here's one superposition, here's the orthogonal superposition, and those are the basis states of our qubits, where L is plus or minus 1. And here's how we represent a general qubit vector on the Bloch sphere using Laguerre-Gaussian modes notation. So there's our first qubit, and then if we take plus minus L equals plus minus 2, then this is our second qubit basis, 0 and 1, our third, and our fourth, L equals plus minus 3, plus minus 4. Notice that there are twice as many intensity lobes as the azimuthal index number. And a multi-qubit superposition, such as a 4-qubit superposition, could look something like this. This is taking the top row as an equally weighted superposition to form an initial state of our QFA system. So this is one mode that we use, and we do so experimentally in this manner. So our photon source is a type 2 spontaneous parametric downconversion source. Type 2, the pairs are generated with orthogonal polarization, so they can be separated at a polarizing beam splitter. One of them goes to a heralding detector, and the other goes to the rest of the setup, which is a qubit arm, where a spatial light modulator modulates the phase with a phase screen, and then diffraction grading to make a hologram. And then there's also an amplitude carving technique. And notice that this mode is the same as the 4-qubit superposition. Here's a little fancier diagram about incoming light being shaped by a spatial light modulator and having a LG mode in its structure as it continues to propagate through a system. So after being shaped by the SLM, the photon enters the qubit arm, where it encounters a beam splitter loop, which, if it's reflected, there's no change in its structure because it hasn't been rotated. But if it enters the loop, it goes through a Dove prism, which is something that performs a unitary rotational operation on the photon structure. So this operator is applied to each qubit in the superposition, and the photon continues having been rotated in its structure. So if it leaves the loop, this is, we used a 50-50 beam splitter. So half the light gets reflected, 25% of it leaves after one loop, and so on. Then it's been rotated once, and it encounters a second spatial light modulator with a shape that doesn't match up with the shape of the original state because it's been rotated. So then the second detector accepts photons if the phase has been removed, and the measurement mask is the same as the generation mask, except without the amplitude modulation, because you don't need it to perform phase flattening, and the way the photons are detected is being coupled into a single mode fiber that accepts the Gaussian state, which is unshaped. So it's looks like this. So this is rotationally invariant Gaussian mode, and these peaks represent coincidence counts between the heralding photon, which triggers a detector and waits for its qubit pair that's flying through the qubit arm, and it takes, well, the delay is about 45 nanoseconds to begin with, and then each of the beam splitter loops is about 60 centimeters, so successive loops are delayed by about 2 nanoseconds. So that's what we're seeing here is coincidence counts in the time domain. And here is for Gaussian photons. So they decay at about 50% each loop, which is what's expected with the 50-50 beam splitter. But if we put a qubit structure onto the photon and rotate it such that after, say, 5 loops, it returns back to itself, it's rotated by 72 degrees by the Dove prism, then the overlap of the photon structure with the initial state in loops 1 through 4 doesn't match. So the accepting probability is decreased. It doesn't couple into the single mode fiber as efficiently. But after 5 loops, you notice that the shape of this peak is about the same as the shape of the Gaussian. And this is the principle we use to perform prime number searches. And here we're searching for the prime number 5. So here are some results that demonstrate the principle with a single qubit. Here's the ±1 mode. And here's 3 different angles of the Dove prism. So the Dove prism actually rotates the structure by twice its angle, and the Dove prism angle is what's in the title of the graph. So the structures rotate by 18, 36, and 72 degrees. And the accepting probability is the overlap squared, which for n qubits is the sum of cosines, and then you square that because the sine terms drop out of the inner product. So single qubit measurements produce this. Of course, the period is doubled, and the sinusoidal function with twice as many lobes. And it's tripled and quadrupled. So here's for our 4-qubit basis that we used in our calculations. And for multiple qubits, first we saw that with a 2-qubit quantum finite automaton, if the state had 180 degree or 360 degree rotational symmetry, such as a superposition of sorry, this should be 0 and 4 here, 1 and 3, 1, 3 here. But anyway, you can just visually look at this plus this and see that it has 180 degree symmetry. And we notice that the accepting probability returns to, well, it's measured to be near 1 again after 5 loops, which is more efficient than a single qubit going through the same process. And also, this is one of the measurements that we demonstrated low decision error. So this is below 30% at least in a prime number search. So these are accepting probabilities. So these are erroneous because it's not the prime number equals 5, it's prime number equals 1, 2, 3, 4. Each rotation is reading a character from the input string. And after 5 loops, the accepting probability returns to near 1. So here, this is written correctly again. Here's our 4-qubit superposition. So these are measurements for 360 degrees. This was for 180 rotation. So in summary, we've demonstrated a photonic realization of a QFA using photons in multiple qubit states. And with further measurements, we, with more efficient setups, we might be able to look for higher prime numbers. So thanks for your attention, and I want to thank the experimental quantum optics team at Alba University. Here we are in the lab. Here we are in the other lab. This is a sauna, actually. And I want to mention also this quantum card game that's really fun. So look that up if you're curious.
Thank you, Stefan.
Thank you too.
Basically, you have a question about structured photon. This is also main technology you mentioned. One is maybe explain more. I am not sure we have time for this. But second question is, can we generate structured photon with the help of microwave cavity? And also, what other methods of generating structured photon?
Yeah, so let's see. Here I think, so if you imagine a laser beam, then if you send a laser beam at a spatial light modulator, then its profile will be affected by the spatial light modulator, which can affect the phase, and you can also implement an amplitude modulation technique. So if you put a camera here, you would see this shape in the laser beam, right? But the photon structure on the quantum level, the field carries the wave function information, which carries the information about the probability distribution in position of the photon. So a structured photon has some probability to be measured at some position like this. So over time, if you put a measurement screen at the same place as your camera was for the laser beam, the pattern you'll see is this, built up by individual photons. So most of them, I mean, they'll be most likely hitting this bright spot, and some of them will be hitting the other parts of the photon.